Nowadays, we have all kinds of complex tools in distributed systems, like Kafka or RabbitMQ. Message brokers everywhere that help systems talk to each other. But have you ever wondered what simple idea made all of this possible in the first place? Before distributed systems and cloud infrastructure, it always started with a basic communication pattern, a producer sending data to a consumer. And at the OS level, that pattern is powered by something called inter-process communication, or IPC. In this video, we're going all the way back to the basics, and I will show you how pipes work to connect processes together and let them share data. After that, we'll write some code breaking it down step by step. Let's jump in. But what are pipes in IPC? And although we can use other tools to perform IPCs, such as sockets or shared memory, we'll focus more on pipes on this video. We can think of pipes as a message tube that connects different programs or processes running inside a computer. Linux users use pipes all the time when using terminals such as cat file.txt pipe grep hello world. So this is basically two processes or two programs being used with the pipe command. The cat is getting the content from a file and the grep is filtering it. Just like how you might put a message in one end of a tube and someone receives it at the other end, pipes let one program, we call this program a producer, send information through this virtual tube to another program, which is the consumer, that is waiting to receive it. Think about it like that. Program A has some data it wants to share. It drops the data into the pipe and program B picks up that data from the other end of the pipe. It's a simple but powerful way for programs to talk to each other and work together while they're running separately on your computer. This workflow follows the same principles of the producer-consumer model. And the key element of IPC, pipes establish a unidirectional flow of information, which basically means that data consistently moves in only one direction from the write end to the read end of the pipe. Pipes are used in a variety of system-level programming tasks, such as data streaming, which is when data needs to be streamed from one process to another. Pipes offer a simple and effective solution. Inter-process data exchange. Pipes facilitate the exchange between processes, essential in many multi-process applications and in command line utilities, for example, as we saw before. Pipes are often used to connect the output of one command line utility to the input of another. This way you can create a powerful command chains. And why are pipes so important? First, they offer modularity. They allow specialized programs that can build something really well to chain that data to another program or process efficiently. Instead of one massive program, you get reusable components. And efficiency. Data flows directly between processes. No temporary files or intermediate storage are used. The OS handles the plumbing. Speed mismatches. Built-in buffering lets a fast writer keep going even if the reader is slow, or vice versa. No blocking, no data loss. Simple but powerful. One line of code in your terminal connects complex operations. Let's now understand pipes versus Go channels, because you might be thinking that pipes are basically like Go channels, and you're not quite wrong. They do share some similarities. What do they have in common? They're both used for communication. Pipes let different programs talk to each other, while channels let Go routines communicate within your Go program. And data transfer, whether it's between processes, pipes, or Go routines, channels, both are about getting information from point A to point B. Synchronization. Both provide a level of synchronization, which means that they can make things wait. Writing to a full pipe or reading from an empty pipe will block the process until the pipe is empty or and the data is sent to it. In a similar way, receiving from an empty channel in Go will block the Go routine until the channel is ready for more data. And buffering. Pipes and channels can be buffered, which means they can start data before the receiver is ready. A buffered pipe has a defined capacity before it blocks or overflows. And similarly, Go channels can be created with a capacity, allowing a certain amount of data to be held without immediate receiver readiness. And the differences are direction of communication. Regular pipes only go one way, like on one-way street, for example. But Go channels, they work both ways by default. Channels in Go are bidirectional by default, allowing data to be sent and received on the same channel. Ease of use in context. And well, channels are built into Go standard library, into Go really, and they just work. While pipes need more setup since they're an operating system feature. And when to use pipes? Let's say you need different programs or processes to talk to each other, and maybe even programs written in different languages. That would be a great fit. Or you are working with separate applications that need to share data. Maybe you are on Linux or Unix and want to use the system's built-in communication tools. And when should you use channels? You're writing concurrent Go code and need Go routines to coordinate communication. Or you want a simple, safe way to handle concurrency in your Go program. And you are building a complex concurrency patterns like worker pools or fan-in or fan-out operations. That would be great fits for using channels. Let's now understand how pipes works in Go. And Go makes working with pipes pretty straightforward through the standard library. In Go, you face two different types of pipes. The first one is in-memory pipes. This type of pipe, they lives while your programs lives. And the io.pipe function is commonly used to create a synchronous in-memory pipe, which means that it lives entirely in your program's memory. It's synchronous, meaning that when you write data, it goes directly to the reader without involving the operating system. It's just a fancy way to connect two channels, read and write underneath your code. Let's see this code on the standard library so you can understand better. Here I am at the Golang official source code, and let's search for the pipe which is inside the IO package, which is the input output pipe.go. So here it is. As you can see, this is the pipe struct, and you have a writer channel and a reader channel on pipe struct. And when you declare a pipe, that's basically what it's doing, right? It's making a reader channel, a write channel, a reader channel, and yeah, the done channel. And you will receive a pipe reader and a pipe writer, which basically wrapper for the pipes. And here it is. As you can see, the read will receive an array of bytes, and you'll also work a lot with the write function, which will input an array of bytes too. So that's basically it. Of course, you have to close it. So yeah, that's basically it. io.pipe, it's just a fancy way of connecting two channels together, right? When we talk about OS level pipes, we're actually using real pipes that the operating system manages. When you need real pipes, use os.pipe function, which internally is using the sys underline pipe to syscall, and the standard library handles all the complexity underneath for us. Let's see this code on Golang start code. So that's the function to create an actual OS pipe in Go, and it's returning a pointer to a reader and a writer too. And however, let's declare inside our code and actually see what's happening, because it will be much easier. And if we go right here in this internal function, it will, yes, in this function we will have an actual raw syscall to the kernel, which is doing the sys underline pipe to syscall. So yeah, this is an actual OS feature that you're performing in your Go code when you're calling os.pipe. And now you understand the comparison of in-memory pipes and OS pipes, and how to differently create them and what happens under the hood. So if you think that you are learning something out of this video, subscribe and leave it a like below, and I promise you on the next video you will learn much more. Now you know 2 ways to make pipes in Go. However, there are other ways, and we will actually make an OS pipe with another function Go. So stick out to the end. Let's see the overall architecture of it and how it works. So that's the overall idea of the consumer producer model, right? So in one end, you have a writer, which will, well, write data inside the pipe in one end of it. And on the other end of it, you will have a reader, which will raise the data that the writer is sending through the pipe. And we do have type of pipes. The first one is anonymous pipes, which are the simplest type of pipes that you may face. They are temporary connections, and they name it pipes. So the anonymous pipes, they are temporary connections, and they only exist while your program is running. They're used for communication between parent and child processes, and once the process ends, the pipe disappears. Let's see in code how that works. Let's actually write a pipe of this type. So here I am on my IDE. So let's start. I will make an OS pipe first. So it will return for me and reader, a writer, and an error, as you can see. Actually in production, treat this error, right? However, I won't do that. And I will just use an cat command. Let's use that. Now I will, well, set the command's standard input to the pipe, which basically means that with this command, I can get a bunch of things, and I can get the standard input of this process. So everything that inputs inside this process, I will send to the reader, right? So reader will be able to read everything that will be input to this process. And I can get the standard output too. However, the standard output, I will set to OS standard output. And I will start the command. I can write to the standard output. So this is receiving a byte. So yeah, hello from parent. Yeah, let's send this message. Writer dot close. So we will close the writer, and I will wait. So yes, the writer will send the data to the standard output, and the reader will read, because everything that's being input to this process will get read. So yeah, let's run this. So as you can see, however, this is an OS pipe. So we are actually making a pipe. So yeah, it will get made inside your operating system and it will be deleted right after the process finishes. However, we can make an input out. Well, let me just show you guys one thing. You can actually write a string to that. You don't actually need to write bytes. So yeah, you can do that too, as you can see. And let's make an IO pipe. This, well, this doesn't return an error, that's it. Yes, it doesn't return an error. However, we can't write a string. We do have to send bytes for it. Yeah. Yeah, as you can see, that's two ways of making anonymous pipes in Go. Let's now understand about named pipes or FIFOs. And unlike anonymous pipes, named pipes are not limited to live processes. They are not temporary connections. They stay in your file system even after the programs finish. So any process can connect to them by name, making them useful for communication between completely unrelated programs or processes. And as IPC can sometimes be an abstract concept and challenging to understand for those new to systems programming, let's use a simple and relatable analogy to make this easier. Let's picture a busy coffee shop order system. So we will have consumers, which will be the producers. They will producing orders. They come up to place their orders, which get written and lined up in a queue. And the baristas, which will be the consumers of this order system, they will grab the order from the queue or the pipe one by one to make the drinks. And during morning rush, the orders pile up faster than the baristas can make the drinks. That's the full buffer. And the customers might have to wait for this buffer to free up some space to place some more orders. During quiet afternoon hours, baristas stand around waiting for new orders to appear. That's an empty buffer. The order queue or the pipe keeps everything organized and handles the timing mismatches between when people want to order and how fast baristas can work. Whether it's crazy busy or that quiet, the system keeps flowing smoothly. So let's make this example in code. Let's make a named pipe now. And I will store the path of our pipe on a variable. And this path will be related to where the pipe will be created. And I will create inside the temp folder, which is related to, well, all files created here, they are temporary files. So that's just a great practice. And I will check if the file exists, and we can do that using the os.start function. I will actually create a helper function for that, and pipe path, which will be string return a bool info or os dot start function, which will give the file info for me. And if I have any error right here, I will just return a false. You can treat this better in production, but yeah, you can do that. And I can get the file mode inside the file info, and I can't do that if I want to mode name it pipe. I can do that. You can just do that if you want to, but if you want to perform a faster operation, you can do a bitwise here, and it will well, if all the bits is not 0, it means that it's not a named pipe, right? So let's, if not exists, it's because, well, it doesn't exist. So we will create one, name it pipe found at cough shop f, and we can create one. And I will just call a function inside the Unix package, and this Unix package, you actually want this one, not this one. And you will have to download this package, but I have downloaded previously. But yeah, you will have to actually download it. And I will just pass the path that I want to and the mode of the file. Yeah, sure. And I will give my user read and write permissions, the group read and write permissions, and everyone else read and write permissions. You can uh, make a different mode based on your use case if you want to, but I don't need it. Error while creating pipe. Let's do like that. Yeah, and I will return println file created. Let's test that. So yeah, the file is created. Now let's check if the file is actually created inside my temp folder. I want to check the type of the file too. So as you can see, I have some files here, some temporary files. And yeah, our pipe is right here. And as you can see, this is the type of this file, which is P, which stands for pipe in Unix systems, in Linux systems, right? So that's how you make pipes, named pipes in Go. Let's now make some actual orders inside our pipe, right? So yeah, I just realized that the name is not correct. So yeah, the first thing I'm gonna do is actually open the file so we can, well, talk to it somehow. And I will open file and I will pass the path and the permissions, which will be this one, and mode, name it pipe. So if I have any error, I will just print the error, printf, and error while opening, name it pipe. So yeah, that's it. Now we have to defer close this thing. And I will declare a wait group so we can send some orders inside that and, well, have a way of synchronization. So let's start by producing orders. So I will get the wait group and the coffee orders, which will be the file. And well, we can get the actual orders, right? And it can be only a string, but let's pass an array of strings. Let me differ this. So yeah, I will range inside my orders. And for each order that I have, I will write the order inside my pipe. Dot right. We can do right, but yeah, we have a string, so let's just write this thing here. Should name it pipe. Yeah. I don't want to break it if any errors happens, uh, because, and I will have a finishing task to say that, well, the turn finished or whatever, end of day, doesn't really matter. Let's just send a finish. Sure. So now we have to find a way to consume that. And we can't consume this order. Of course, we have to get the wake group and the coffee orders too. And that's the only thing that you really need to do. I mean, a simple way, right? You can make a lot of fancy things if you want to. No big deal. I, I will have a scanner, which will be a buffer of input and output, and I will just instantiate a new scanner. And for each, I will pass my coffee orders. As you can see, this thing, it receives a reader and the OS file implements the interface. So yeah, I want to iterate inside that. I just realized that the name is not correct. I'm gonna scan inside this thing, and for each scan, I will get the text that is being sent. And the first thing I want to check if it's not finished, which means, well, the order is finished. That, I mean, if you want to finish the thing, you can keep like listening to the pipe like forever if you want to, but I will implement like that. If the order is finished, yeah, let's print coffee orders break. And otherwise, I will just println it's processing this order. So yeah, basically just that. I will check if any error is happening while on the scanner. So yeah, sure. We can now perform, we can call this thing, and I will add like two tasks to our wait groups, and I will spawn that inside the routine, our produce orders, and I'm passing the wait group and the coffee orders, which is my file that we just opened. And this is an array of strings. So let's pass an espresso and Arabica, why not? Latte, and I don't know, cappuccino. Go consume orders. Wake group, coffee orders. Yeah. And we will wait for that to be processed. So I think we should be fine. Go run. Let's run that and see what happens. So yeah, it processed way too fast. You can like I don't know, process a little bit slower if you want to. Times 2, let's say. So yeah, on a real production environment, let's say that you are like transforming data, you are actually getting data somewhere, and you are making some operations in, when you are consuming it from the pipe. So it can take a couple of milliseconds. So that's a little bit more real, right? So that's one way to consume, produce orders, and to produce and consume from pipes. Now, what I will do is I will make this thing a little more fancy, because in a production environment, you don't want to be listening like forever, or yeah, you want to treat this thing better. Timeout. And let's get everything inside that and copy. Go mod tidy. So yes, what I'm gonna do right here, I will just I will add a timeout. So the first thing I'm gonna do, I will write a receiver channel, which is the time. And yeah, I don't want to wait forever for in order to happen, right? So the way we can do that is actually we can like select here, and in case we have a, in case the timeout is reached, we can just, let me print timeout reached, stop being order processing orders, let's say like that, and just return, because I don't want to be to, in a lot of cases you don't want to listen like forever. Yeah, let's do like that, and let's sleep right here. So that's the average case, and I'm gonna pass a timeout for that. Timeout, I mean, timeout after I don't know, maybe 10 seconds. And let's pass the timeout to the consumer thing. Go run main.go. It's not gonna time out. However, if I increase the time here, it will time out eventually. So the timeout reached and it stopped processing orders, and it didn't process it the cappuccino one because each one was taking like 4 seconds. So yeah, that's a much better way to work with pipes. So if you liked today's video, leave it a like and subscribe below, and just tell in the comments what you want to see in Golang. See you later.